Hello, my name is Priyadarshini Subramaniam, or Priya, and today I will be talking about neural networks for the binary classification of chronic kidney disease diagnosis using biomarkers. Since the publication of the U.S. Kidney Disease Outcomes Quality Initiative, or KDQI guidelines in 2002, chronic kidney disease, or CKD, has been recognized time and time again as a leading public health problem. In addition to affecting the kidney, it is correlated with many secondary conditions, such as end-stage kidney disease and cardiovascular disease. Currently, CKD affects more than 13.4% of the world population. Current diagnosis methods involve monitoring of the patient's GFR and creatinine values. Upon the steady decrease of an individual's GFR level for 3 months or more, one is diagnosed with CKD. Herein lies two major issues. Most patients with CKD do not display symptoms at the early stages of the disease. Hence, it is difficult to detect the disease at its early stages, resulting in delays in diagnosis and eventual treatment. In addition, GFR is a function of the blood creatinine level, which only provides a snapshot of the kidney function at a particular time point. This creatinine level can, therefore, vary depending on body size, muscle mass, and other time-sensitive factors. With these two problems at hand, it is crucial that more accurate methods are developed to diagnose CKD earlier on in a non-invasive manner. To aid in solving this problem, a binary classification convolutional neural network was developed using PyTorch's functionalities to accurately diagnose a patient with CKD. Using data collected over 2 months at Apollo hospitals in Karaikudi, Tamil Nadu, India from 2015, a convolutional neural network was made to classify CKD diagnosis using 24 features, of which 11 are numerical and 14 are categorical. These features, their labels, and their corresponding data types can be seen above in the table. The dataset includes numbers from a total of 400 patients. After cleaning up the data, which included removal of missing values, categorical to numerical transformation, and normalization of all values, the dataset only contains 203 rows. This can be seen on the bottom. The dataset was then randomly split as a 70% training dataset, 20% validation dataset, and 10% test dataset. Ultimately, this resulted in 141 samples in the training dataset, 41 samples in the validation dataset, and 21 samples in the test dataset. An epoch number of 9,000 and a learning rate of 0.003 were initially used as a starting point for analysis to result in the best model. Further analysis of these specific hyperparameters are included later on in this presentation. To calculate loss, PyTorch's BCE with logits loss function was implemented, as they are optimal for binary classification tasks. This function calculates the binary cross-entropy loss of the training and validation datasets. Lastly, ReLU layers were used to be sandwiched in between linear layers in the neural network. When starting development on the neural network, the optimal number of linear layers was first determined between 1, 2, and 3 linear layers. The results of these can be shown here. An ideal loss curve should show a validation curve that sits above the training loss curve, showing that the validation process optimizes the system. Looking at figure 2 here, it is apparent that the 3 linear layer neural network shown on the right possesses this quality, making a 3 linear layer system a better fit for our purpose. You can see, however, that some parts of the validation and training loss curve overlap on the rightmost loss curve, which is uncharacteristic of an ideal loss curve. To correct this, dropout layers were implemented. Dropout layers make a certain percentage of the activation functions null to result in an overall more robust model. Both the 25% and 50% dropout rate were implemented, as shown below. After implementation of the dropout layers, it is apparent that the validation loss curve dips below the training loss curve at some points. This implies that the validation function doesn't optimize the neural network after initial training, making this model less ideal than a neural network without dropout layers. Thus, dropout layers were not implemented in the final neural network. Finally, to result in a more robust model where the validation loss curve sits strictly above the training loss curve and doesn't intersect with the training loss curve, the hyperparameters were optimized. These results can be seen at the top of the slide. With a smaller learning rate of 0.001 and a considerably larger epoch number of 18,000, the validation loss sits strictly above the training loss curve and doesn't interact with the training loss curve at any point. This can be seen at the top figure on the right. This is a more ideal version of the loss curve, which helps us determine that the following set of conditions are the most optimal for our neural network. 3 linear layers with the inclusion of sandwiched ReLU layers with the learning rate of 0.001 and an epoch number of 18,000. Here on the bottom, you can see the results of the finalized neural network. You can also see that the test accuracy is 21 out of 21. This shows that while using the test dataset, this neural network correctly predicted the CKD diagnosis of 21 out of 21 patients that were in the test dataset. At the top, you can see the structure of the final neural network. Though the results obtained were very close to ideal, there is still potential for improvement. The dataset size, after removal of all missing values, was not large enough for a production-level binary classification project. Binary classification convolutional neural networks of this type require at least 1,000 samples, according to sources online. Alternatively, fine-tuning of the model may also be acceptable. Lastly, here are some of the references and resources that I used for the completion of this project. Thank you very much for listening.